So good morning, good afternoon, good evening, wherever you may be. So today the usual host is the speaker, so I'm hosting for him since he's visiting me here in Florianopolis. So it's my pleasure to introduce PIOTR HAJAC from IMPAN, who's going to talk about computing associated projective modules using the Milnor clutching. And the floor is yours.
Okay, now I'm unmuted. You should hear me all right. So for starters, let me express my deep gratitude to the Federal University of Santa Catarina at Florianopolis, and especially to Gilles for fabulous hospitality. I'm really very happy to be able to stage our seminar right here on site. It's always so much better to give a talk in person than just purely online. So thank you very much, guys. I'm also very grateful to the organizers of the seminar for inviting me to give this talk. So Piotr, thank you very much. Well done. And without any further ado, let's rock and roll. First disclaimer is the following. This research theme, if you wish, was present in my scientific life from the very beginning. And it is about doing K-theory of projective modules that come from quantum principal bundles. And today I would like to show you how one can use, in special circumstances, two different methods of computations and how you can use it to derive some really nice non-commutative geometric conclusions. The first part of my talk, up to a commercial break, is basically a recall. It's not a total recall, but it will be a pretty thorough recall because it's been something that I've been doing for a quarter of a century. So it was really hard to prepare this talk because I had to compress like 25 years into 10 slides. It's not so easy, but somehow something came out of it. And I will review it, and only in one case I will really give credit. So you see, this talk is based on our recent joint work with Francesco, Tomek, and Bartek. We just posted it on the archive in December. And I would like to focus on a certain new result and its application. But first 45 minutes or so will be devoted to the general context. And of course, where else to start if not in the classical setting? And to focus attention and avoid mistakes, let everything be compact, and sister algebras let be unital. So I have a compact house of principal G bundle, and I have a representation of my group G, but I don't assume it to be a Lie group. I also don't assume a local triviality of X. It need not be locally trivial. I just take a finite representation of this compact house topological group. And now I can construct the so-called associated vector bundle. It's done in the following way. I take the usual Cartesian product of my space and my vector space, and then I divide it by the action of G. And the action of G is defined over here, right? It's a right action of G. So because X is a right G space, of course, I just act with G on the right on X. And by using the representation and the inverse of G, I act on the left on my vector space. So this gives me a right action. I take these equivalence classes, and this is by definition the space of the associated vector bundle. And now this construction defines a monoidal functor from the category of finite dimensional representations of G, where you can tensor representations, to the category of vector bundles over the base space, because of course you can take tensor products over fibers, and you can thus obtain the tensor product bundle, tensor product of vector bundles. Well, but in the setting in classical differential classical topology, let me say, that doesn't have to be differential geometry. Of course, differential geometry is where you have so many nice examples and applications, but you don't need any differentiable structure for what I'm talking about. So you had the reverse effect in the classical topology, namely, whenever you are given any vector bundle over some, say, compact Hausdorff space M, and you have a typical fiber V, well, then there exists a GLV principal bundle Fe over M, which is called the frame bundle, such that when you perform this association procedure, and here, because you start with GLV, your representation is just identity, then you recover the vector bundle started from. So basically, every vector bundle is an associated vector bundle, classical topology. It's not the case in non-commutative geometry, but let me get back to it later. Okay, now in the non-commutative setting, so for starters, let me briefly recall what I mean by compact quantum spaces. They are just given by unital sister algebras. And by the first one, non-commutative vector bundles are encoded by finite projective modules over these unital sister algebras. And now if you want to define a compact quantum principal bundle exactly in the spirit of Voronovich and his definition of a compact quantum group, well, you say that this is a unital sister algebra equipped with a free coaction of a sister algebra H of a compact quantum group. And the freeness is defined by Elwood's density condition, which is spelled out for you right here. And if you would translate it into a commutative setting, that's basically the cancellation property. Okay. And well, I call it Elwood's condition because this was first published by Elwood, but it's verbatim the idea of Voronovich in defining compact quantum groups. Because it's not so obvious having a compact quantum semigroup to define the inverse of an element to say that it's really a group. And Voronovich did it by saying, all right, so I have a compact quantum semigroup with left and right cancellation properties, and then it must be a group. So basically, the very compact quantum group is defined by the freeness condition on its own multiplication. So using the same idea, Elwood defined a free action of compact quantum group on a unital sister algebra, which is exactly this density condition. Okay, but now in order to go to the realm of Hopf-Galois theory, where you have a lot of technology, well, again, we do very much the same what Voronovich did for compact quantum groups. You see, Voronovich created the Peter-Weyl theory for compact quantum groups. He, using representation theory, he defined the Peter-Weyl Hopf algebra for his compact quantum groups. And much in the same fashion, we constructed the Peter-Weyl functor, which maps a compact quantum principal bundle, which is given in the sister algebraic setting, into a principal O of H comodule algebra, where O of H is exactly this Voronovich Hopf algebra, and the principality of its coaction is tantamount to the existence of a strong connection. You can simply prove in the spirit of Hopf-Galois theory that the canonical map must be bijective and strong connection is its partial inverse. I'm not going to give the axioms for a strong connection. Well, there is this device called a strong connection, and if it exists if and only if your comodule algebra is principal. You can take it as one of many possible definitions of principality of your comodule algebra. And because it's something that we are going to use for K-theory, let me, instead of giving you the usual definition, which I can spell out for expert, you say that the comodule algebra is principal if the canonical map is bijective, the fixed point, the coaction invariant, and the algebra is faithfully flat over the coaction invariant subalgebra, and the antipode is bijective. But it's a bit of a mouthful. So this is why at a certain moment, with the blessing of Hans-Jürgen Schneider, who is like a key person in Hopf-Galois theory, we baptized it as principal comodule algebras. But you can take as a definition that there exists a map from the Hopf algebra to the tensor square of this comodule algebra with a bunch of properties. It must be unital, bicollinear, and when you follow it by the multiplication, it's the same as applying the co-units. I just spelled it for you. It's not very complicated. But I cannot write everything. I only have 20 slides. Okay. And now, much as in the classical topology, given a finite dimensional co-representation of my Hopf algebra, and here I'm taking a left one, one defines the associated projective module of a fixed point sister algebra in the following way. This is given by the cotensor product, okay? And cotensor product is by definition the difference kernel. So basically, these are these elements in the tensor product of P of A tensor V, such that the right coaction on the left leg agrees with the left coaction on the right leg. And you shouldn't be surprised by this definition, because here I'm defining this sort of space of my non-commutative vector bundle as a subspace of something. And in the classical setting, well, it was defined as a quotient. And this is typical thing that happens, that quotient constructions in classical topology go into sub-constructions in non-commutative geometry or topology. Okay. So now it's a very nice fact, because I like this linguistic pun, strong connection and strong monoidality. But you can actually show, and this is in my paper with Paul Baum and Kenny DeCommer, that the existence of a strong connection on this O of H comodular algebra P, so principality, is actually equivalent to the functor induced by this principal comodular algebra, the contensor product functor, which you can view as a functor from the category of finite dimensional co-representation of the whole algebra of H, the category of B by modules. It's equivalent to this functor being strongly monoidal. So not only it preserves the monoidal structure, but you have a natural isomorphism built into it. Okay. Now, of course, you have a sanity check if you take the commutative setting in the construction above. So A is just continuous functions on some compact Hausdorff space X, and H is continuous functions on some compact Hausdorff group G. Then this axiomatics for a compact quantum principal bundle says that X is a compact Hausdorff principal G bundle. And then the associated module is nothing but the section module of the associated vector bundle. Okay. So here, this is what I mean by this notation. My base space is X mod G, the space of orbits, and I'm taking global continuous sections of the associated vector bundle. And this is by Sir Swan, a finely jetted projective module, and well, you can check that it agrees exactly with this construction, which works in full generality. Okay. Now, one thing is to define your objects, and another thing is to somehow classify them, distinguish them. Because it goes without saying that when we go into vector bundles, we're interested in the K-theory classes. And it's the same story in non-commutative topology, okay? So, well, so for starters, when you can prove that indeed it's always the case that, and it's in full generality. So I'm no longer referring now to any sister algebraic setting because there are many more principal comodular algebras than you have objects in the image of a Peter-Weil functor. I mean, not every Hopf algebra is cosemi-simple. So this world is a bit larger. What is important is that the Peter-Weil functor brings the sister algebraic setting, which encodes classical topology, into this comodular algebraic setting, and the condition of principality, the condition of a canonical map being bijective, is actually equivalent to the freeness condition of Elwood, which was a very hard theorem to prove, but it's done. Okay, so now let me discuss it in full generality of principal comodular algebras, and I use script letters to somehow emphasize that I no longer assume that anything here is a sister algebra. It might be, but it doesn't have to be. Okay, because in this setting we always have that well, O of H is a Hopf algebra, P of A is a comodular algebra of this Hopf algebra, but the fixed points is always a sister algebra. Okay. The idea actually behind this Peter-Weil functor is very beautiful. Imagine that you have your total space of the bundle, and you are taking functions which are polynomial along the fibers, but continuous along the base. Okay? And in the classical setting, there is a very beautiful way to realize it. You can just construct the associated vector bundle when your vector space is the Hopf algebra of your group. And then it's because your fiber is actually an algebra, you can multiply the sections, okay? And if you use appropriate topology, not the usual topology coming from operator algebras, from sister algebras, then continuous sections will give you exactly this Peter-Weil comodular algebra, okay? Okay. There is another way to view this Peter-Weil comodular algebra. Whenever you have an action of a compact group or a compact quantum group on a Banach space, and the sister algebra is usually a Banach space, you can decompose your Banach space into so-called atypical components. But this decomposition is in the category of Banach spaces. So your direct sum must be complete. It's not an algebraic direct sum. So basically what this Peter-Weil business does is that you algebraize this direct sum. So you still have direct sum of all these atypical components given by an action of your compact group, quantum or not, but you no longer complete it. It's just algebraic sum. Okay, but this is somehow the intuition behind being algebraic along with hyper. Okay, so this is just to give you the intuition. Okay, so we know that in full generality, whenever V is a finite dimensional left comodule and there is a principal H comodule algebra, you always have that this is a finite generated projective module. Okay, this is not difficult to prove. And now, well, this allows you to do the following. I apply my condenser product functor, and to every finite dimensional co-representation, I assign a finite projective module, so I can take its K0 class. Okay. Of course, these are modules over coaction invariant subalgebras. Maybe I wrote it, but I didn't say it. Okay. So the moment you apply this cotensor product functor to get K0 class of a finitely generated projective module, then you can apply the usual Chern character as defined by Alan Kohn. This is called Chern-Kohn character. Also, Max Karoubi contributed a lot in this context. And then when you compose these two arrows, then by definition, what you obtain is what with Tomek Brzezinski we decided to call the Chern-Galois character, because it has its Chern part here and its Galois part there. But very much like in the classical setting, when you have Chern-Weil theory for principal bundles, this composition actually is very computable. The way that you do it here, if you really want to compute this composition, well, you cannot just give me an abstract finitely generated projective module. You should give me an idempotent that represents this model. And once I have an explicit idempotent formula with entries from this algebra B, well, I can use this explicit formula for the Chern character. I can build something like a cyclical cycle. And interestingly enough, the natural construction before you take like a multitrace, you land in matrices over B, because your elements of your idempotents are in matrices over B. They are not in B in general. Okay, so but when you construct this cyclical cycle at the beginning, it's given by matrices, but then cyclic homology is obviously Morita invariant, and then you can take this trace, and then you land in the usual cyclic homology of the algebra. So that's how you compute it. So you get something very explicit. But it turns out that, in fact, much like in the classical setting, the calculation really largely simplifies. Okay, so how do we do it in the classical setting? You take your principal G bundle, then you take the Lie algebra of your structure group G, okay? And then you take G invariant polynomials on this Lie algebra G. And because whenever you take a connection on your principal bundle, then you can take its curvature. Then the curvature form it's on the total space of the principal bundle, but it's equivariant. And because these polynomials are invariant, okay, then when you plug in this connection curvature 2 form into these invariant polynomials on the Lie algebra, what you'll get an invariant form on the total space, but it's the same as having a de Rham form on the base space. And then you can verify that this is closed, so you can take its de Rham class. Okay, and this is how Chern-Weil theory is defined in the classical setting. And lo and behold, we have something very much similar here. But these replacements are not so obvious. I mean, we already know this was great discovery of Alan Kohn that you have to replace the Rham cohomology by cyclic homology of the function algebra. But this replacement is not so obvious. I mean, of course, there are formulas, but it's not simple-minded. And on our side, on the Galois side, this replacement of invariant polynomials on a Lie algebra is also not straightforward. If you want to understand it better, ask Tomek, because Tomek wrote this part in our paper explaining the relationship of a space of cotraces to this Lie algebra setting. But for us, it's just the space of cotraces, okay? And as I defined it here, this mysterious object, you take all elements in your Hopf algebra, more general coalgebra, which is symmetric under the application of the coproduct. And somehow for experts in quantum groups, let me mention that it's totally non-obvious what this space is. Take quantum SU2 and give me this space of cotraces. It's done by the Japanese guys, but these are deep, complicated theorems about these little Q-Jacobi polynomials. There's a lot of deep representation theory, I believe, going into this business in order to write down explicitly what the space of cotraces is for, say, quantum SU2. But conceptually, it's something very easy, okay? And indeed, whenever we have a cotrace, we can take a strong connection. We apply a strong connection to a cotrace and we get a cyclic cosine, okay? And we can take it cyclic homology class. Again, we can prove that it's closed. And the cyclicity by this construction is guaranteed precisely by the fact that we don't take an arbitrary element of algebra, we take a cotrace. And when we iterate applying the coproduct, blah, 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 strong connection, then it will have a cyclic, it will be invariance as it should have in cyclic homology. So that's a very explicit construction, which is just at the level of principal comodular algebra. You don't have any vector bundles here, you don't have any representations. But lo and behold, whenever you have a finite dimensional co-representation, you can take its character, okay? And here's the definition. So I choose any basis of my vector space. Then I take a matrix for the coaction in this given basis. And then I take the trace of this matrix. And of course, the trace does not depend on the choice of the basis, like in the classical setting. Okay. So to every co-representation, finite dimensional co-representation, I can uniquely assign an element in my Hopf algebra called the character. And of course, this is a cotrace. Yeah? It has this property of being symmetric when you apply the coproduct. And then when you compose, well, everything here is commutative. I really like that the non-commutative geometry diagrams are typically commutative. So that this is the kind of commutativity we want to keep. And now this is really very computable. So if you look into my paper of Tomek Brzezinski, the formula for the Chen-Galois character is really very compact, very neat to write down. However, what we are today interested in is not this formula computing the invariance, but you see the title of my talk is to compute associated projective modules. So the way we really compute this Chen-Galois character, I mean, prove that you can decompose it in this trend-wire theory, is that first and foremost, using a strong connection, we determine an idempotent representing this module over here, okay? And this is the main theorem. Everything else, the formula for the Chen-Galois character is just a corollary. That was the tough cookie to prove. And it's even quite complicated to write it down, but okay, let me spell it out. So a setting is the following. We have a principal H module algebra, we have a strong connection, and you can prove it's not very difficult, but you always have kind of a left B module retraction of inserting the subalgebra B inside the algebra A. Okay, so there always exists a unit of left B module map. So in particular, note that when sigma is restricted to the subalgebra B, it's just the identity. Okay, it always exists. You can actually construct it using a strong connection. So you can give an explicit formula, right? And we need it here to formulate this theorem. Well, now it's just a question of the bookkeeping. I know that it's pretty ugly to take a vector space basis of some infinite dimensional algebra, but it's just, you know, for writing things out for the bookkeeping. So let P mu be a basis of A. Of course, it's typically infinite. I take the dual basis. After all, it's a vector space, so it makes perfect sense. And then I define this auxiliary map. In fact, what this auxiliary map does, it computes for me the right coefficients. You see, the idea is that in order to have some uniqueness in writing down a strong connection, remember, a strong connection lends, let me go back to this formula. you land in this tensor product, okay? But you can also, it's a sum, it's a tensor product. So I can write 0 in many different ways. I can write x tensor y minus x tensor y, and then x tensor y can be in any nonsensical part I want to, okay? So then it's just very prudent to say, all right, I want every element in the left leg of my tensor product to be basis elements. Then by linear independence, once I choose my basis, everything on the right is uniquely determined. And this R mu, once I fix my basis of this algebra, R mu just computes this right leg, the coefficient which tends to a given basis element. And then the way of writing a strong connection is, well, it's not canonical, depends on the choice of the basis, but at least there are no ambiguities, and you can draw some conclusions as to where the legs of a strong connection must be. Okay. So this is this R mu. Of course, I still have, as always, a basis of my vector space V, my representation vector space, because I need this matrix, okay? And well, I know that I'm writing this definition over and over again, but it's good always to have it in front of the eyes. So I choose a basis, and then I take my coaction, and then I have this n by n matrix with elements in my Hopf algebra. All right. And now, within this paradigm, we claim that the matrix, which is defined as follows, it's double indexed, okay? For every I and j, I can apply a strong connection, okay? And for every I and j, I'll have some finite sum. But this sum can be bigger or smaller depending on my I and j. But in any case, a finite sum of finite sets is usually finite. So this is what I denote by my capital N. There will be a finite number n such that this will be a square matrix. And now look how it is defined. Well, I apply my strong connection, then I compute the right coefficient. I put the right coefficient on the left, and I multiply it on the right with my basis elements with respect to which I take my coefficient. But then, in general, I cannot claim that this lands in coaction invariant subalgebra. Okay, so this is why I have to apply this sigma. Left bilinear map, which is unital. Well, and then I claim that having this construction, this is an idempotent matrix. And most importantly, this is the idempotent matrix which realizes my associated projective model. Okay. So this is how, using a strong connection, you can explicitly compute an idempotent representing your projective model. And this is what you can now plug into the formula for the Chen character of Alan Kohn, the Chen Kohn character. Okay. And things get much simpler when you are one-dimensional. Then your co-representation is just given by some group like G, and there is no IJ, yeah, because this is a one-by-one matrix. And when this is a one-by-one matrix, well, basically you can write your strong connection always in such a way that R mu is equivariant with respect to G. So right, the coaction of R mu will give me R mu tensor G, and the coaction on L mu will give me L mu tensor G inverse. Okay, so now when I flip the legs, remember, a right leg of a strong connection goes to the left, and left goes to the right, and then you multiply. But here, because I know where these legs of a strong connection land, there's no IJ index, okay, which messes around. If I have something which is G inverse covariant and something is G covariant, so multiplication will give me something invariant. So I don't have to apply this sigma. I mean, I can apply it, but it's identical on BA. Okay. So here the formula simplifies, and in fact, this formula was known much earlier. It was easy to prove. What we struggled with Tomek Brzezinski at the beginning of the millennium was to generalize it to an arbitrary dimension. But here's the answer. Okay. So this is a way to compute your idempotent matrix from a strong connection, and it works in full generality. And I will tell you later on in the case study of quantum complex projective planes how we computed it using a strong connection in the context of my application. So this is why I'm recalling it. Okay. Now, on the other hand, let me remind you the brilliant construction of Milnor. When Milnor defined his celebrated connecting homomorphism in algebraic K-theory, well, basically the story is that if you give me two free modules, I can glue them into a projective module. But for starters, let's consider a pullback diagram of algebras. It cannot actually be rings, but I want to use tensor products, so let them be algebras. For me, there will be sister algebras, but Milnor was much more general. Okay, so I just consider the pullback diagram of algebras and a certain module automorphism. I take V to be a finite dimensional vector space. So B12 tensor V is just a free module. And I take an automorphism of this free module. Okay. And well, now one can prove that if you take the following pullback, because you can just compose pi1 tensor ID with chi. Okay, so you are taking the pullback construction here. Well, it looks a bit funny because one module is over B1, another module is over B2, then the bottom module is over B12. But you can actually prove it's very easy that the pullback is now a module over the pullback algebra. When we do it very simple, it's just, I don't know, it's obviously a pullback in the category of vector spaces. So you have a pullback in category of vector spaces, so you know what it is as a vector space. And then it's very easy to see that actually this pullback vector space is precisely a module, in this case, this convention left module over the pullback algebra B. That's just a trivial exercise, okay? What is not so trivial is to prove that this is a finite-generated projective when V is finite dimensional. But that's part of this brilliant construction of Milnor.
Excuse me, Piotr.
Yes.
Can you remind me what this M of B1 tensor V B, what this M is?
Yeah, in fact, by definition, it's the pullback. This is exactly what I just explained. By definition, this is the pullback. Okay, I'm giving you two linear maps. One is the.
I understand. Yeah.
Yeah. And then a certain small miracle happens that this pullback vector space is in fact a left module over the pullback algebra V, and that's all you know from the definition. This is easy. But what is really beautiful and spectacular, and what Milnor proved, is that for starters, this is finally generated projective, and secondly, when you take K1 class of this invertible matrix here, then whatever choices you make, you will not change the K0 class of this finite-generated projective module over there. This is why we, at the end of the day, obtain this connecting homomorphism from K1 of B12 to K0 of B. You know? So that's the depth of Milnor. But okay, in order to be, you see, here I answer your question in a very explicit manner. Okay, but you should think about this M as you see, this is the clutching construction of a projective module, and before we had this associated module construction. But in both cases, at the end of the day, in order to do some classification, to determine some aspect of K-theory, what we need to present these modules via explicit idempotence. And here, this explicit idempotence are given by the strong connection, and in the Milnor case, this explicit idempotence is given by the so-called Milnor idempotence. And by the way, here it's a funny historical remark, because for Milnor it was too trivial to write such calculations. But it was necessary to really take advantage of his beautiful theory. So we computed it, but then it was obvious to us that it was not a new result. And then in Oberwolfach, we met Andrew Ranicki, who is a famous topologist. And he told us, oh, yes, I computed it 20 years ago, and it's on my site. And indeed, it is on his site. But because he didn't bother to publish it, well, we cited him, and we published it, because it's very important to have an explicit reference. Okay? And in fact, but it's really, it's a breakfast exercise. It takes maybe 2 pages to compute. But it's really a high school student exercise. And once you really see how you prove, when you look into Milnor's proof that this is finely generated projective module, okay, then you can immediately compute this projection, right? But I think that this formula is absolutely beautiful because it's a very simple polynomial formula. And you see, just bear in mind that at this stage, so here I didn't assume anything about my pullback. But now, like you see, if you want to have a Meyer-Vittori 6-term exact sequence in K-theory, right, you need your pullback to be at least surjective on one side. Otherwise, it doesn't work. If you want to apply the RAM principle, your pullback diagram in terms of algebras or push out in terms of spaces has to be one surjective for algebras or one injective for spaces. Otherwise, there is no relation between topologies of the pieces and topology of what you glue. Okay, so it's very important that at least one of these maps is surjective. And here we choose pi2 to be surjective. And it's very important that chi should always go towards things that are surjective because we want to go and we want to lift. Okay, so I cannot reverse the direction of chi. And then, well, because pi2 is surjective, I can take this invertible matrix A, which is the matrix of chi, right? I mean, how do I get my matrix A? This is a certain automorphism, automorphism, okay? So by choosing a basis, I explicitly get a matrix in GLV, an n by n matrix. And once I have this matrix, well, it's an n by n invertible matrix with entries in my algebra B12. And now I can lift this matrix because, of course, you have pi2 by assumption surjective. I can lift it. On one hand side, I can lift my matrix A to matrix C. So simply I have a matrix C in B2, and when I apply row 2 component-wise, I get all the entries of A, and I can always do it, okay? And then I do the same with the inverse of A. But because this is a lifting, which is, say linear, but I don't assume anything else. In the context of sister algebras, you might keep things self-adjoint, whatever, but it's not important. What is important is that C and D are no longer mutually inverse. They might be when everything trivializes, okay, but they need not be. That's the whole beauty, okay? So when they are not invertible, these expressions like DC or CD are non-trivial. They are not equal to 1. And well, you can check that in full generality, this matrix is always an idempotent matrix. And as I told you, as Ranitzky proved, and as we computed, this Milnor projective module, which is obtained by the clutching with the help of chi, is precisely the projective module given by this, what I call Milnor projection, or Milnor idempotent. I shouldn't say projection, there's no star structure here. All right? And this is a very explicit formula, and it's a polynomial formula. So you see, if you're familiar with K-theory or sister algebras, you know that whenever you have a 6-term exact sequence of sister algebra, you have associated, whenever you have an exact sequence of sister algebras, you have the associated 6-term exact sequence in K-theory, all right? And there is a map which goes from K1 of one sister algebra to K0 of the other sister algebra. But this is basically like taking a unitary and applying the logarithm and searching for a self-adjoint element such that the exponent is this unit. These are very complicated analytical things. Okay? And there is, you can relate just a short exact sequence to a pullback diagram. There is a relationship between them, which is pretty standard. And for instance, in Hickson and Rowe book, you can find it as an exercise, how you relate pullback diagrams with exact sequences. So you can make some translations here. And so my point here is that the usual formula that you know from K-theory of sister algebras is very complicated. This formula is beautifully polynomial. And here I must tell you another historical remark, even more important, because Milnor defined his connecting homomorphism for algebraic K-theory. And as everybody knows, algebraic K-theory and K-theory of, say, sister algebras or Banach algebras, they coincide for K0, but not beyond. Already K1 is different, okay? But the same formula, the same idea of Milnor works for sister algebras. And somehow it was mentioned in passing by a paper of Nigel Hickson, and I forgot, there's a guy in Hawaii. And they had a joint paper and somehow mentioned in passing, but not very explicitly, that this should work. So one day I had an opportunity that Nigel was visiting me at IMPAN, and I put him behind my desk and told him, you are not leaving my office until you write the proof that it works for sister algebras. And within 20 minutes, the proof was written. We put it into our paper, citing, of course, Nigel Hickson as the author. And now it's published. I mean, you have a precise proof that this formula works for K-theory of sister algebra. So in other words, Milnor connecting homomorphism, which was constructed to begin with in algebraic K-theory, works just the same way in sister algebraic K-theory. But you really have to be careful here because K1 is a different animal for sister algebras than for just rings. In algebraic K1 is not the same as sister algebraic K1. But they are closely related. Simply, it's the same space, but divided by different equivalence relations. One is smaller, one is bigger. So you have to make sure that things are fine. You just do some diagram chasing, I don't know, 5 lemmas.
Excuse me, Piotr. So the
Yeah.
only difference is the closure, yes? You take a commutator
No.
and you take
No.
a closure, yes?
You take in sister algebras, you divide your group by the connected component of identity. And if you do it in algebraic K-theory, you somehow divide it by commutator. And one is smaller, one is bigger.
Yes, but there is also a formula using this commutator, but you have to take a closure.
It's not a question of closure. It's a question of really different relation, I believe. I don't believe it's a question of taking a closure.
The closure of this commutator subgroup, but you need to use, as far as
maybe.
I remember, GL.
I never went so deeply into this. I don't remember. Maybe,
okay.
Maybe you're right, but anyway, we never used it. Okay, even if you are right, which I'm not sure you are, so what are you saying that that the connected component of identity is the closure of a commutator subgroup?
But not for unitary, but for GL over arbitrarily large matrices. Probably something like that. But I'm also not 100% sure.
Doubt it. Somehow it's against my intuition. If there is an expert on this who can weigh in, you're welcome to do. I just don't remember. So let's not waste time for it.
Okay.
We can look it up. What is most important is that we have a solid proof due to Nigel Hickson, which is like half page long, which translates from algebraic K-theory to sister algebraic K-theory, right? And this is a typical theme. Remember what Atiyah and Hirzebruch translated what Grothendieck did to topology, right? So it's much in the same spirit. What is important is that I have a pullback diagram of sister algebras. Then I have a 6-term Meyer-Vettoris exact sequence in K-theory, and this is my connecting homomorphism. In algebraic K-theory, there's no 6-term, there's no periodicity. You have this long exact sequence, but you still have a connecting homomorphism from K1 to K0. Okay, and now here it is. Here how it is defined. Since A is invertible, again, whether it's algebraic or sister algebraic, it's a class of an invertible matrix over your ring or your algebra, for a sister algebra. And what do you assign to it by definition? Well, you assign to it this Milnor module, the K0 class of this Milnor module, but you somehow subtract the rank here. So remember that PA is a 2n by 2n matrix, but we started with n by n matrix. Okay, so somehow subtract the identity matrix, which is of the size, which is the same as the size of your matrix A. All right. And given this formula, well, you know that it's well defined in K theory. So if you choose a different basis and you'll have a different representative in K1, different A, then you will get a different PA. But still, when you look at the classes, it will always be the same formula. Okay. So this is the famous Milnor connecting homomorphism, and that's what Ranitzky and us computed to be an explicit formula for the idempotent that realizes the construction of this Milnor clutched module. Okay, now a commercial break. I have to acknowledge the sponsor as usual. I know that you guys are seeing it the millionth time, but again, my visit here this time is also sponsored by this project. And you see Floripa is highlighted here. And because of this funding, I can give this talk from here. Yeah. Okay, but now the legal requirement has been fulfilled. Then go on. I acknowledge the sponsor. All right. So now I begin my talk. Let me see what time it is. Yeah, perfect. Perfect. Ha, I'm halfway through exactly as intended. So now my talk...
Piotr, hi, it's Ludwig, hi. So I was not at the beginning, but you mentioned our paper, I understand, with Hatfield, right?
I mentioned that...
At the beginning, I missed the beginning of... So all this was in this paper, probably, right?
I don't think all this was in this paper. I'm basically relating here 25 years of my scientific life because that's something to do with Mark Riefel in Berkeley, and I was always interested of how you obtain projective modules as associated with compact quantum.
Okay, I understand that. Yeah. Okay, but I have in mind this with Mattes and with Wagner, no, this final paper. I think all this is there.
Yeah, but these are examples, right? There's no theory, which I was referring to. Here mostly, Ludwig, you see, I use here the following since you missed the beginning, and we are not...
Okay.
Okay, so this is true that yes, okay. So in this sense, of course, you're absolutely right because this one was computed in our paper. You're right, Ludwig.
Yes.
Milnor part in our paper, so you're absolutely right. But I just said at the beginning that I'm going to use so many different papers from 25 years of work that I cannot give credit at every single step.
Okay.
I gave credit only to this theorem with Tomek Brzeziński, which gives explicit formula.
Yeah, that's another stuff. Okay.
That's another stuff. But you're absolutely right, Ludwig.
Thanks.
We computed it, and this was exactly our paper in the Banach Center publication. Yes.
Okay, thanks.
Yeah, sure, thanks. Okay, so now...
Excuse me, I have a question about the idempotent you were explaining. Yes. No, the idempotent matrix M2N. I lose the page. One page. Yes. I was computing the trace of this idempotent, and it was amazing that, for example, even when C and D are 1 by 1 matrix, I think that the trace of this matrix is 0. How can it occur that an idempotent has 0 trace?
I don't believe you must have done something wrong. The trace should be N.
Sorry?
The trace should be N because it's like rank N projection.
So maybe I don't know the definition of this notation of 1C2. What is the definition of this quantity 1C2 minus DCD?
Well, to have a definition of 1 and 2, you better ask Bertrand Russell. But for the D and C, you just have them defined as the liftings, right? I have an invertible matrix over the sister algebra B12, and I lift it into a general matrix, not necessarily invertible, typically non-invertible, but over the sister algebra B2. And I lift it using the surjection pi2. That's it. Yeah.
I think the question is about the comma between 1 and the C bracket, perhaps.
Yeah, okay. Thank you, Ludwig. You see, remember that B is given as a pullback algebra. So it's the sister algebra of compatible pairs. And you can easily see that these pairs are compatible, because imagine that I apply pi2 over here. Well, when I apply pi2 over here, I have dc, which is now A inverse A, which is 1. 2 minus 1 is 1. And then C times 1 times D is now A times A inverse, which is again 1. 1 equals 1. And then we're here, well, 1 minus dc will be 0. 1 minus dc will be 0. So you can see that it is indeed in the pullback. Yeah. You have,
yes.
These are compatible pairs. Yeah.
Okay, thank you.
You're welcome. Okay. All right. So now let's assume a specific situation in which our principal comodular algebra is piecewise cleft. So I have a pullback in the category of H comodular algebras. And again, I'm now completely general algebraic. It doesn't have to be in the image of a Peter-Weil functor. Remember, in the image of a Peter-Weil functor, you always get a principal comodular algebra, but a very specific one. For instance, your Hopf algebra is always cosemi-simple, which is not always. You can have plenty of beautiful principal comodular algebras for non-cosemi-simple Hopf algebras, like for roots of unity, right, Ludwig? You have very nice Hopf theory at roots of unity, and these Hopf algebras.
We have this example, I think, for roots of one, no, in our papers. Okay, yeah. Okay, thanks.
All right. And now somehow you should think about it. It's not exactly true, but the intuition is that I'm looking at a principal bundle which can be trivialized just by a covering consisting of two sets. That's the idea. Okay. It's not completely true, because cleft and trivial are definitely not the same things. But the upshot is that whenever your comodular algebra is cleft, the associated module is not only projective, it's free. Okay, and this is a very well-known fact. Okay, but let's do it slowly. So I have a pullback in the category of comodular algebras, and now I assume that these comodular algebras P1 and P2 are cleft. What does it mean? It means that there exist cleaving maps, which are maps going from Hopf algebra H to this comodular algebra Pi. Again, like with a strong connection, I don't bother to give a definition. Let me just mention that they have to be unital and collinear. But what is absolutely fundamental about them, you assume them to be convolution invertible. And what do I mean by convolution invertible? Well, whenever I have any linear map from a coalgebra to an algebra, I can define the convolution product of these linear maps exactly as given by this formula. Okay. So what do? I co-multiply. So I go from C to C tensor C. I apply the tensor product of my linear maps. So I land in the tensor product of A with itself, and then I multiply. And this gives me again a map from C to A. This is a convolution product. And because coaction is co-associative, and because multiplication, not coaction, co-multiplication is co-associative, and multiplication is associative, this convolution product is again associative. And it's not a big deal to verify that having first a co-unit going from coalgebra to the ground field, and then having a unit, inserting the ground field in the algebra, that this is the neutral element. That's very easy. And what we are assuming here, we are assuming that this map is convolution invertible in this sense, okay? And let me just mention that whenever this is an algebra homomorphism, it's automatically convolution invertible, because convolution inverse is given by precomposition with the antipole, okay? But you, even in the completely classical setting, and even doing something as simple as S1 fibration over RP1 with Z2 structure, you will have a non-trivial example of something's being cleft but not trivial, and you'll have an example of a map which is so this will be a Hopf algebra of functions on Z2. This will be the sister algebra of functions on the unit circle. And you have convolution invertible map from this two-dimensional algebra to this infinite-dimensional algebra, but it's not homomorphic.
The co-invariant superalgebra is the same for all of them?
No. Co-action invariant, not co-invariant. No, it's different for each and every one of them. It's you think about it in the following way. I have my principal bundle and I chop it into pieces, say 2 pieces. but these two pieces intersect. So basically I have three pieces, left piece, right piece, and the intersection piece. But of course the base is also different, right? So each base is also different. Okay. So now what can I conclude? Well, for starters, we have a very general theorem with Elmar Wagner about principality, the pullback of principal coactions. It's really in full generality of C-Galois extensions, if you want. Our theorem says that if P1 is principal and P2 is principal, if the two coactions are principal, then the pullback coaction is also principal. This is a very difficult theorem, in my opinion. And the way we prove it is that given a strong connection on P1 and a strong connection on P2, assuming just that one of these maps is surjective, we construct a strong connection on P. And if you want, this is an equivariant version of Milnor. Yeah, because remember, strong connections can be used to compute explicitly these idempotents, okay? And here we are doing it before taking the cotensor product with the co-representation. When I do the cotensor product co-representation, here I get a free module, here I have a free module, here I have a free module, here I have a projective module. And after, when I have this explicitly given co-representation, I will land in the Milnor picture. But we generalize it because in the sense that we don't care about representations, it's the setting of principal coactions, and secondly, and this is actually most important, we don't care about P1 or P2. Our theory works for arbitrary principal coactions. They don't have to be cleft. Here I want them to be cleft so that I can apply Milnor. But to compute, say, projections idempotents from a strong connection, we don't need it. Okay, I'll be more explicit later on in an example. So we are in the setting that we have a piecewise cleft comodular algebra. And then automatically this is principal. Why? Well, because if you have a cleaving map, then you can very easily convince yourself that the cleft comodular algebra is obviously principal in the trivial way. Okay, and then because these are cleft, they are also principal, and by this general theorem with Elmar, we know that this is principal. Okay, so that's the setting now, right? And in the setting, we'll have the main theorem, the new theorem, which we just achieved like in December, November, and submitted it to the archive. Okay. So now, as I promised to you, I'm taking, and I see that here I changed the notation from A to P. Okay, doesn't matter as long as I'm consistent on a given page. So that's in the category of comodular algebra. So all maps are equivariant. So this means that I can apply the cotensor product everywhere, right? And now this will give me a pullback diagram in the category of modules. It will be simply the Milnor setting if you want, okay? Well, definitely I get a pullback in the category of vector spaces, and I'll have the same situation as before, because it will be a module of one coaction invariant subalgebra, another one, but at the end of the day, this will be the module over the pullback of these coaction invariant subalgebras. Because on one hand side, this pullback induces the pullback of vector spaces, but also I can take coaction invariant subalgebras everywhere. It will again be a pullback of coaction invariant subalgebras. So we kind of land back in the Milnor settings. And as I mentioned, because by assumption P1 and P2 are cleft, and because P1 and P2 are cleft, P12 is automatically cleft because Pi2 is a surjection. I'm not that sure you need to know that is a surjection, but anyway, P12 is also automatically cleft. Then you know that all these three associated modules are free. I hope I'm making a sound difference between 3 and 3. These three modules are free. Okay. And here's a beautiful picture which I designed with Tomek and Francesco, beautifully typed it up into LaTeX, which really shows how we have a Milnor picture of his associated module. So if you want, the back wall of his spatial diagram is exactly what I had before. Only here I somehow write the identity map between these two modules, okay? So that I have a square. But basically it's equality, so it's this triangle which I had before, yeah? So this part is my back wall of this cube. But now, well, because I had these cleaving maps, all right, I can write explicitly isomorphisms of these modules with the free modules. Let's not bother about formulas. They are simple formulas which are afforded to you by the cleaving maps.
Sorry.
No, they are isomorphisms. They are isomorphisms. I'm somehow telling you explicitly in what way these tensor products, these associated modules, are actually free modules. If they are free modules, I should be able to write them in such a way, and I am. And I have an explicit isomorphism which is afforded to me by the cleaving map. I didn't bother to write it down, but it's really not a big deal. Yeah. And now you can see that it's a free module of a coaction invariant subalgebra.
But in any case, it's written down in the paper.
Oh, yes. Of course, it's written down in the paper. Thank you, Francesco. And now, basically, when you look at this diagram, you can say, well, so now that I honestly and explicitly write these associated modules as free modules using these isomorphisms given by cleaving maps, well, I can define chi to be such that it renders the whole diagram commutative. Well, it's kind of obvious how it works. I go by this lambda 1, 1, 2, and then I come back by the inverse of lambda 2, 1, 2. And because I have explicit formulas, this computes for me chi. Okay? And this is this explicit isomorphism, and that's precisely what you need in the Milnor clutching construction. Okay? And this brings us to the main theorem. So this is the take-home message that's the small new thing that we accomplished recently. Technically, it's not a very big deal because basically this diagram is a proof of this main theorem, but I love the applications that it has. And this is why the remaining time will be devoted into applying this theorem into studying of K-theory of quantum projective planes. But okay. We phrase it in the context of sister algebras. Of course, we can do it for principal commodule algebras, and who knows, maybe for principal coactions in the C-Galois context, I don't know. But here our motivation was to study K-theory of sister algebras. The motivation was to unravel generators of K0 groups of certain sister algebras. So this is why somehow I like to start here in this sister algebraic context. So I say that I have a compact quantum group in the sense of Voronovich, and that I have a pullback diagram in the category of unital H sister algebras. And I also assume that this pi2 here, as before, I assume it to be subjective. Then I also assume that when I take the Peter-Weil commodule algebras of A1 and A2, they're both cleft, and their cleftness is witnessed by the cleaving maps gamma 1 and gamma 2, respectively. As usual, I take V to be my n-dimensional left commodule, and this is over this Voronovich's Peter-Weil algebra. So here I wrote script H. I could have written this script O of straight H. Okay, and then our theorem is that this associated module can be expressed by the Milnor idempotent. And that's not a big deal because I showed you the Milnor picture of this projective module. So obviously, you can write such a formula. The taste of this theorem, the essence of this theorem is that we compute this invertible matrix A out of representation matrix defining a representation, defining a collection. Okay. So that's here is really what the theorem is all about. You see, I take my left comodule V, so this is some finite dimensional co-representation. I choose any basis. I write the left coaction again as before. I have this representation matrix UKL. Okay, so for every KL, I'm in my Hopf algebra, and now I can apply both cleaving maps gamma 1 and gamma 2. It's just that one lands in the Peter Weil of A2, another one lands in the Peter Weil of A1. But then I apply these surjections pi1, pi2. Yeah. I will explain it. This is a very good question. Yes. Yeah, but you have to use the convolution inverse. Okay, yeah, but convolution inverse is also a map from a Hopf algebra to the algebra. You don't change where it goes. The domain and codomain are the same. All right. So now both of these maps, pi1 gamma 1 and pi2 gamma 2 inverse, where this is the convolution inverse, they both go from the Hopf algebra into the Peter Weil comodule algebra of A1 2. So Peter Weil of the sister algebra. Okay. So it makes sense. I can multiply. One is an algebra, one is a Hopf algebra. I can multiply. I can take the convolution product. Okay. And well, by definition, this is now a matrix which is with entries over B12, right? This is an n by n matrix with entries in B12. And also you can prove that this is invertible. Yeah? It's an invertible matrix. And I claim that this is precisely the matrix which then can be used for the Milnor idempotent to give this associated bundle. So that's the essence of the theorem, right? Give me a representation or a co-representation defining this association. So this gives me abstractly a finely generated projective module, all right? And then because I'm in this piecewise cleft setting, I can use my cleaving maps to compute out of this co-representation an invertible matrix over the sister algebra B12. And this is precisely the matrix with the help of which I construct my Milnor idempotent, which gives me exactly this module. So that's the essence of this theorem. That's the novelty. This is a take-home message. If you have any questions about it, this is a good point to ask. Okay. Okay. And now we are going to examples. So we work in the setting of quantum complex projective planes, so CP2s, but we do it in two settings. One is Waxman-Soibelman, so we are talking graph sister algebras. But another one comes from these multi-push-out quantum complex projective spaces. And these are animals which, with Bartek Zieliński and Arthur Kaigun, we discovered them ages ago when considering the following problem. You see, you have something given to you classically, like complex projective spaces, and then you can consider deformations that preserve different features of your projective spaces. So when you go to Waxman-Soibelman, well, this is the quantum group picture, right? These are obtained from Waxman-Soibelman quantum spheres, and of course, Waxman-Soibelman quantum spheres are obtained from quantum unitary groups. Okay, so you deform your ambient unitary groups to quantum groups, and then you get spheres, and then you get projective spaces. So this is how you get these projective spaces. Our setting was completely different. It came quite surprisingly from lattice theory. I will not tell you the exact historical story how it happened, because it was kind of a random walk, but I want to give you the mathematical essence. So at a certain moment, well, we realized that there is a concept of a free distributive lattice of n generators, okay? And this is a problem which is open since 19th century. So this is the only time in my life that I cited a paper which was published in the 19th century, okay, 1890 something. Okay? And the thing is that it's still an open problem. What would be a formula to express, like the Stirling formula for n factorial, right? You have an analytical formula which gives you the asymptotics of combinatorial formula. So you can ask yourself how many elements you have in a free distributive lattice on n elements. And it's obvious that it's less than 2 to 2 to n, which is a very fast growing exponential number. And things were explicitly computed, up to some 9, 10 generators. 2 to 9 is already a big number. But as of now, there is still no, as far as I know, okay, there is still no answer to this problem of what is the asymptotic formula for this combinatorial algorithm. But anyway, this is an interesting problem in itself. And what is quite remarkable that any projective space, in particular complex projective space, when you take its canonical affine covering, this canonical affine covering of a projective space will give you automatically a model of a free distributive lattice on n generators. Okay? So we wanted to have a deformation of a complex projective space that would preserve this property. That now when I go from the lattice of affine coverings to the lattice of C-star ideals in my non-commutative C-star algebras, that this lattice of ideals, and remember, in algebra it's not true. Ideals do not form distributive lattice in an algebra, but they do form a distributive lattice in a C-star algebra. That's because for C-star algebras, I times j is equal I intersect j, which is not true in pure algebra, because you distinguish I squared from I. For C-star algebras, I squared equals I. Okay. So for C-star algebras, I have a free distributive lattice. I have a distributive lattice of ideals, and our main result was that our deformation preserves this property. So the lattice of ideals, which we kind of get by construction, is free distributive. Okay. So this is how we got this multi-push-out or multi-pullback deformation, depending whether you look from the point of view of spaces or C-star algebras. And these are sort of the animals that can be obtained by taking Yuan fixed point subalgebras of what we call Higord quantum spheres, which are, if you want, they are not graph C-star algebras, but they are higher rank graph C-star algebras. Okay, but it's irrelevant. I'm saying it because there are many people interested in graph C-star algebras. Okay, so for starters, before I go into projective planes, because I want to define them as fixed point subalgebras of the 5 spheres. I have the diagonal U1 action here. I have a diagonal U1 action there. I go into fixed points, and I can take it as the definition of my projective planes. The initial definition for our projective spaces was different. I told you it came from combinatorics, but when we did like inverse engineering, and when we discovered these spheres, such that then when you take the fixed point algebras, you go back to the C-star algebras we're playing with, but that's a separate story. Okay, right now all that you have to remember is that here you have pullback diagrams of Yuan C-star algebras, of unital Yuan C-star algebras. If you are wondering as what these dots indicate, well, they indicate the location of the U1 action. So here the U1 action is on the rightmost component, okay? And here you have a U1 action which is diagonal. So you have U1 action on teplitz, and you have U1 action on this. So maybe I should explain all the ingredients. So B4Q is a Hong-Szymański quantum ball. It's a certain C-star, it's a graph C-star algebra. All right. Yeah. For people doing graphs, I can actually draw a picture. So let me try it. So when I go into S5, this is my graph. Right? So this is S5. The graph C-star algebra of this graph is the CS5Q. And when you go to Hong-Szymański quantum 4 ball, basically it's very much the same thing, but you have to remove that circle. So the graph C-star algebra of this graph is the Hong-Szymański quantum ball. Okay, and you can view it, what is nice, as a subalgebra in the Teplitz tensor Teplitz. So obviously standard notation for Teplitz algebra is calligraphic T. So these guys are Teplitz algebras. Okay. Well, I don't have to explain the circle and SQ2. Okay, so now, and this is, if you want, this is the Hilbert sphere. Probably the simplest way to explain these odd-dimensional Hilbert sphere is the following. You take an appropriate power of Teplitz algebra, and you divide it by the same power of compact operators. And you can this is what Voronovich once explained to me, and I cherish this memory very much, because what is this tensor power of Teplitz algebra? Is a multi-disk. What is a multi-disk? Topologically is a ball, right? And what are compact operators? These are like open disks. So when I divide a closed multi-disk by the open multi-disk, well, I'm removing the inside of a ball from the ball, so I get a sphere, right? Of one dimension less. Okay? So basically, this is not the way we defined it. Okay, but it doesn't matter. But these are the sister algebras, and you can show that they are higher rank sister algebras. Yeah. But that's just an explanation of what these animals are over here. All right. Yep. So as is written here, it is straightforward to verify that the two subdiagrams involving the bottom arrow are commutative. So you have one diagram here and you have another diagram there.
Piotr, can I ask just maybe one more comment? Just ask a question. So F new, you didn't say what are these F?
No, I'm not going to, because it would take too long.
Okay.
Well, here you can guess it's a coaction, right? But already here kappa comes from a gauge trick, and it would take way too much time to explain it. Okay, I is the inclusion iota, but we have explicit formulas that render this diagram commutative, and the only thing that you check is that this is commutative and that is commutative. Then by the universality of the pullback construction, everything else is commutative. And in particular, you have a unique map F, which connects these two pullback algebras, okay, by the universality of a pullback construction. So it exists, and is all that you check. This is why I need formula. That's commutative, and this is commutative. Then the rest is automatic. Okay? So F exists and is unique. All right. But this is all equivariant, so now I can go and take fixed points. And when I take fixed points, as I told you, kind of by definition, I get my projective spaces. One is with Waxman-Soibelman, and one is Hilbert. And by the way, this is this beautiful notation which was introduced by Tomek in our paper. When I restrict my morphism to a fixed point subalgebra, I just write F with a superscript, which indicates the symmetry. Okay, I hope it's self-evident. Now, when you take the fixed point of SQ2, of course, you get the standard Podlesh quantum sphere. This is the famous quantum Hopf vibration. Here, you just kill the circles, right? And here, by definition, get the quantum complex projective plane of Waxman-Soibelman. And now, when you look again, here you kill the circle and kill the circle. And here, because it's diagonal action, you get something ugly. We denoted as P1 sister algebra. It's something ugly. This is not CP1H. No, this is not the Hilbert quantum complex project line. No, but it has the same K theory.
And also, Piotr, can I mention two things? That the interpretation is that this is a tubular neighborhood of CP1 in something bigger. And this construction is actually generalized to any dimension, but in a different paper, which is still a preprint.
Yeah, I couldn't agree more. Thank you, Francesco. That's the advantage of having your co-authors. Yes, absolutely right. Yes. You remember, this is a quantum disk. So this is like taking the Cartesian product of a free sphere with a disk. So I'm kind of taking a tubular neighborhood of a sphere. But remember, this is contractible, so K theory doesn't change. So that's the intuition you should have behind this picture. Okay. All right. And now let's go to the K theory. You see, the idea is that there is a more or less straightforward theorem, which was probably proven well before we did it, that if you have that these maps here, mu, this one, and this one, if these three maps induce isomorphism on K theory, then using, like 5 lemma and so on, you can easily prove that also this one induces isomorphism on K theory. And this is what we use time and again. Because it's not obvious here that you have isomorphism on K theory, not at all. And K theory is non-trivial, it's Z3. But here you can do it somehow step by step. So first you prove it here, but again you decompose it into pullback. There's a lot of stuff behind it, but these are the details I'm brushing under the carpet. But using standard technology, you just prove that indeed this is an isomorphism on K theory. But it requires a lot of calculations using pullback diagrams. So this is why I call it a theorem, right? But I do know that this particular map gives me an isomorphism between both K groups. Okay. But now what do we know about K theory? So basically, if you look into, say, this diagram, this is a pullback diagram, which is one surjective. Only this one surjective, that's an inclusion, it's not surjective. But it's a one surjective pullback diagram of sister algebras, so you can apply the Meyer-Vittori 6-term exact sequence. Okay? And when you write down explicitly the Meyer-Vittori 6-term exact sequence in K theory, you will observe that well, one thing is that you get K1 is 0, but another one you observe that the K0 of the pullback sister algebra is nothing but the K0 of this algebra inserted to this K0 group, plus the image of the Milnor connecting homomorphism applied to the K1 generator of the sister algebra. So that's something which we did ages ago in different papers. I mean, for Waxman-Seubermann spheres, it's completely trivial because these are graph sister algebras and these are calculations you can do on a napkin in a restaurant. This is absolutely immediate, okay? And the same holds in this multi-push-out case. So basically, we have this direct splitting into these Z plus Z, which comes from the two-sphere. And then there's interesting third generator, which comes from K1 of a three-sphere. And much in the same way in here. Remember, here we just took the tuple neighborhood, but morally speaking, this is like S2. It's not S2 as a sister algebra, but it has K theory structure of S2. Anyway, it's again Z plus Z, and we insert it into this K0 group, okay? So as I wrote here, the goal is to unravel the generators in the last equations. So all that work was done much earlier, and we know the K groups and we know the generators, but what was still left and was kind of unsolved in 2016 or 17 when we started looking at it, we didn't know what the third generator was geometrically. Of course, you know the K groups. Although I must mention that although computing K groups in the Waxman-Seubermann case for Waxman-Seubermann quantum complex projective spaces is an immediate exercise, even if you don't use graph sister algebra. Because you can get a higher dimensional projective space by having extensions by compact operators. And when applying 6-term exact sequence gives you results immediately, okay? That's very, very easy case. And if you use graph sister algebras, you have everything on the plate completely, okay? But it's when we looked at our sister algebras of these multi-push-out quantum complex projective spaces, even the question of computation of K groups was not obvious. And in an act of despair, I asked Richard Nest for help, and he came to Warsaw and he solved the problem. And I felt very embarrassed because I thought that this problem requires some super duper technology, which Richard has and I don't. But no, I mean, the problem can be solved with basic tools, but it's a very smart idea. So now we have an even smarter idea to compute it. But back then, even computation of K groups in this case was difficult. Okay, I mean difficult. From hindsight, it's easy, but well, it took Richard Nest to help us to solve. Okay, well, but anyway, to cut a long story short, we know K groups. It's not about homological algebra. What we really want is to understand the generators of these groups. What are the classes that really give us these K groups, and what is their non-commutative topological interpretation? So that's the name of the game, is to unravel the generators of these parts of my K0 group, of this third Z, okay? Okay, so this is where we apply our theory. And for starters, well, you have to use what I like to refer to as a prolongation trick. Because if you look here into this part, okay, imagine just apply Peter Weil, right? The problem then is that when you apply here Peter Weil, well, this is by no means a cleft OUH, OU1 comodular algebra. This is the Hopf vibration. Hopf vibration is not cleft. Associated modules are Hopf line bundles. They are not cleft. They are not free. They are projected. Okay. So you cannot apply this Milnor picture advocated before. But you can use this prolongation trick. I can simply observe that U1 is a subgroup of a quantum group SUQ2. So in other words, I have surjection from the Hopf algebra SUQ2 onto the Hopf algebra of U1. This gives me a left coaction. So I can now take the cotensor product, and I have a functor over here of this form. And because I have a diagram which is an equivariant diagram for O of U1, it's a diagram of all U1 comodular algebras, and all of the maps are O of U1 equivariant, I can apply the cotensor product over O of U1, and I can prolongate sort of the fiber from U1 to SUQ2. And I cannot resist the temptation of giving you this intuition, because maybe it's not so completely obvious. You see, you can have a non-trivial bundle, but after you prolongate the group, it can become trivial. Let me give you a very simple example. You have S1. You have S1. Oops. Should be able to right now. Yes. So I view S1 as the edge of a Mobius strip, and I view it over the circle. So this is S1 over RP1. Okay, but it's a non-trivial Z2 principal bundle, right? But now imagine that I view Z2 as a subgroup of U1, and I do the prolongation trick. The prolongation means that I replace my Z2 fiber by the circle. When I replace here this Z2 fiber by the circle, I get the 2 torus. But that's a trivial bundle. You know, 2 torus is a U1 trivial bundle over the circle. Okay, so prolongation typically trivializes bundles. And in full generality, whenever you have a bundle of a form, and it works for quantum groups just the same way. If I have that the total space is a group, and I divide it by the subgroup, then it's a principal bundle with a structure grouping the subgroup, like here U1 and SU2. Okay, but it works in full generality. But now when I prolongate my fiber from a subgroup to a full group, then this bundle is always trivial. And that trivialization is just given by the group multiplication. And it works exactly the same way for compact quantum groups. It's just that you have to apply the coproduct instead of multiplication. Yeah. So that's the trick that we are using over here to guarantee that both legs are cleft. Okay. Here's no problem. This is actually more than cleft. It's trivial. It's just the plain tensor product. It couldn't be more trivial. This is the most trivial bundle. So here is no problem. We are done. Yeah. But now here, because we apply this prolongation trick, now this guy becomes a cleft of SUQ2 principal comodular algebra. I can write the cleaving maps. So now to this diagram, I can apply this Milnor picture and the Milnor construction. But before I do that, so that you understand what I'm talking about, I have to recall some notation. Otherwise, you will not follow my formulas. So, okay, I already mentioned many times the sister algebra of SUQ2. but let me view it as the universal sister algebra given by generators alpha and gamma. Yeah, and we are subject to some relations which most of you know. And now using these generators, I can write the fundamental co-representation matrix of SUQ2, and this is of this form. So this is a unitary matrix in 2x2 matrices over the sister algebra of SUQ2. Okay. Oops, I should finish. Okay, okay. I should finish now, but I'm slightly delayed. But bear with me. Next, whenever you have any unital sister algebra with a Yuan action, then you can define these associated line bundles. These are some spectral subspaces. So you take all elements A, which have this equivariance property. And these are really, if you want, module sections of the associated line bundles for the winding number equal to K, all right? And this is the notation I'm going to use. So in particular, when I have my Waxman-Soberman quantum sphere, then I have LK tilde for a spectral subspace corresponding to the integer K. And in the Higord case, I write the same, but without the tilde. And that's the notation I'm going to use. And finally,
I'm a little bit confused by this lambda, Piotr. So probably it should be the alpha of
lambda. Well, I mean, it should be more or less clear because lambda is in U1.
Yes, but you are taking what? Alpha of lambda times A? Should
Yeah,
it
but
be
it's
like
a standard
that?
notation. I mean, if alpha is an action, then alpha with subscript lambda means an automorphism of A given by lambda. That's standard. And all I do is just multiply by appropriate power of lambda.
Okay, thanks.
Yeah, I agree that if you are very pedantic, you should write alpha of lambda of A, but nobody does. It's a certain shortcut. And please bear in mind that for me, the generating isometry of a Teplitz algebra is S. So S star S equal to 1, that's it. That's the only relation. Okay, so now we can apply this main theorem I told you above to prove what we wanted to prove in a specific case, notably in determining of what is this generator of delta 1, 0 of K1. Okay, and well, it is known that, like in the classical case, the fundamental representation of SUQ2 is a generator of K1 of SUQ2. Right? If you take K1 of a 3-sphere, what is it's equal to Z, of course, and what is the typical generator, the way you write it, of this K1? It's the representation, fundamental representation of SU2. Okay. So it's much in the same way in this case of acute deformation. But now how do we apply this main theorem? Well, on one hand side, what we do, we look at this picture over here. I take the fundamental representation of SUQ2. I take a two-dimensional vector space. Okay, this fundamental representation gives me a left coaction. I do this one more cotensor product here with C2, given by this fundamental representation, and I compute this. And this is an immediate computation, which tells me that what I get is simply L1 tilde plus L1 tilde, L minus 1 tilde. So tautological and anti-tautological line bundle associated with the Waxman-Soberman quantum sphere. Okay. So this is what comes out of this calculation when I calculate the associated module. But the main theorem tells me that this associated module is given by this Milnor idempotent. So the only thing I now have to do is to compute the matrix which gives me this Milnor idempotent. So in other words, I just have to compute this formula. Okay. So now here is my 2x2 matrix over SUQ2 sister algebra. I have my cleaving maps and I compute it. And believe it or not, AKL is just equal to UKL. This is just identity here. It comes out of this particular calculation. That's just the identity. So I know that the representation matrix and this Milnor invertible matrix, clutching matrix, are one and the same thing. So this means that when I apply the Milnor connecting homomorphism, okay, it will be given first by Oh, where is it? Yes. It will be given first by the projective module, which is associated to this Milnor idempotent. But now by this main theorem, I know that this is L1 plus L1 tilde plus L minus 1 tilde. And then I have to subtract this identity matrix, which is the size of my invertible matrix. And here it's 2. So that's the formula. So this is how this main theorem allows us to compute explicitly that, hey, what we wanted to achieve, we achieve. We have an explicit formula here, and this is my third generator. And now, just to finish up, how does it look on this multi-push outside? Remember, we have this commutative diagrams, and we have these pullback structures, and they are related. So in the sense that I have star homomorphisms going from Waxman-Seugelman's side to this multi-push outside. Okay. And this is what I'm going to use. In particular, I have a theorem with Tomek that says that association commutes with taking push forward in K theory, and this is what we use over here. We just know that if you take this given as a projective module, then this funny notation means that I have it is a projective module, but I take an idempotent of this projective module. And then I apply this map component-wise. So that's this notation. So this is, I apply to a matrix, okay, component-wise. Then I get an idempotent of the other associated bundle. This is a theorem that I have with Tomek. It's completely trivial in the classical setting. Well, we proved it for principal commodule algebras, and here you go, right? It's very, very useful to know that if I do my association with exactly the same representation, okay, and I have I have a restriction of an equivariant map, then I push forward by the restriction of an equivariant map will map this associated module to the other associated module on the nose before taking K0 classes. Okay, so taking this into account, I can immediately get this corollary, right? Because I apply this here to that formula over there. And because I know this isomorphism, right? Remember, I wrote it for you somewhere here, that this is an isomorphism. Okay, I know that generators go to generators. So without knowing that it's an isomorphism, I know that I can map this generator here to an element there, but I know that it's again a generator because this FU1 star is an isomorphism. Okay. And the final slide, that's something very quantum. So sorry, I will abuse your kindness by a few minutes, but I find it very interesting. So here is this purely quantum thing, something which is impossible classically. So for starters, ages ago, Japanese guys, I know Masuda, Nakagami, Watanabe, I don't remember all the names, but this was really like the 80s. They proved that, in fact, inside the C-star algebra of SUQ2, okay? You see, this is funny thing. Classically, what you would have alpha alpha star, well, this is a function which has a 0, so it's not invertible. But when you look at alpha alpha star after quantization, there is no 0 in the spectrum. So you can take the inverse of this operator. Okay, so this formula makes sense. It completely doesn't make sense classically. It doesn't exist classically. You can actually argue that there is no function on SU2 which could serve as a generator for K1 of SU2. You can argue it. But here you have it because it's quantum. And then either by computing the index pairing with a certain Fredholm module, or by having a straightforward homotopy argument, which was in our paper provided by Francesco, you can prove that in fact the K1 of class of this W tilde is the same as the K1 class of a fundamental representation. They're just equal in K theory. And as I said, you can do it in two ways, either by index pairing or by homotopy argument. Well, and because they are equal, then the Milnor connecting homomorphism applied to both of them also must agree, right? But now here you can explicitly compute. If you apply the Milnor connecting homomorphism, you see here things are much easier because you are talking one by one matrices, okay? And if you look at these formulas, they are not very complicated. So doing liftings here is not such a big deal. So here using directly this formula for PA, for the Milnor idempotent, directly, you can very quickly compute what is this Milnor projection, okay? Then you can subtract 1, and when you do that, you get this extremely simple formula. And now you should ask a question, what on earth does it mean, 0, something, right? And now look at how I view this CP2Q. You see, this is a pullback of these algebras. So I have compatible pairs. One lives in Podlesh, another one lives in the Hong-Szymański quantum ball. But Hong-Szymański quantum ball is a sister subalgebra of Teplitz tensor of Teplitz, okay? So in both cases, when I'm writing 0, something, I'm either writing 0, something in here, not 0, or 0, something in there, also not 0, okay? But 0, I don't care if it's 0 in this mass or 0 in Podlesh, doesn't matter, it's just 0. But here, I can write something in Teplitz tensor of Teplitz because Hong-Szymański ball is a sister subalgebra of Teplitz tensor of Teplitz. That's why sort of on the nose, these elements look the same, even though they are in the different sister algebras. But this is absolutely remarkable that when you actually do this calculation, okay, so you really apply the Milnor connecting homomorphism. So first you get this Milnor idempotent, and then you subtract 1. You do this calculation, you get on the nose this elementary projection, which is inside the sister algebra of CP2Q. And combining all this above with this preceding theorem, and now we know that this generating element, because that's the image of Milnor applied to U, and this is the image of Milnor applied to W tilde, but class of U is the same as class of W tilde. So this class K0 class must be equal to that K0 class. And here we get a certain miracle, because P tilde is a projection. So this means that this guy is in a positive cone. This is impossible classically, because classically by construction, the rank that you have here is always 0, because somehow you get this projective module and you subtract the rank from it, okay? So the rank is always 0. And classically, there is no vector bundle, okay, which would be a non-zero vector bundle of rank 0, because rank is always the dimension of a fiber, okay? But in non-commutative geometry, we can have projections that are of rank 0 and they are non-trivial. And they are even non-trivial in the sense of K-theory. Not only that they are non-trivial as idempotent, they are non-trivial in the sense of K-theory. So this is absolutely wonderful that you can prove such a thing. You have such an effect. And again, for experts in graph sister algebras, now when I look at it as the graph sister algebra of the following graph, I have 1, 2, 3. Here I have countably infinitely many arrows, and also here countably infinitely many arrows. This is the graph sister algebra of this graph is the Waxman-Soberman quantum's plane sister algebra. And here you have vertex projection P1, P2, and P3. So this P tilde guy is nothing but the vertex projection of P3, okay? If you do identify with graph sister algebra. So it just couldn't be any simpler. Okay, but this is a purely quantum effect. That's completely impossible classically. Well, and now basically what you do, you apply to the theorem above. You apply this isomorphism on K theory, this FU1 star, and you map P tilde into P. And when you look at these maps, which are explicitly given in this commutative diagram, you get immediately on the nose the same formula, because what you are using on this non-zero leg is just the inclusion, which means that it's just identity applied here, right? So don't be confused. P tilde and P are not the same, because this 0 is different from that 0. That's yeah. So this 0 and that 0 are different. And also, if you want, here I view it inside the sister subalgebra. Here I view it in full Teplitz square sister algebra. So now applying this map to that theorem. Well, on one hand side, I get this expression in terms of associated line bundles, and here I get this expression in terms of an elementary projection inside the Teplitz algebra. So this way I get something completely quantum, that the Milnor connecting homomorphism lands in fact in the positive cone. It's itself given as a projection. And really the final statement I want to make, that playing around with index pairing, you can also prove that when you look at these projections, so these are some projective modules over your sister algebras, okay? And these sister algebras are defined as fixed point subalgebras for some compact quantum principal bundle. Okay? But you can prove that neither P nor 1 minus P, and the same for tilde, can be associated with this principal bundle. So that's somehow to show that you have nice, interesting, non-trivial projections in your sister algebra. You cannot obtain them as associated modules, at least for these, background compact quantum principal bundles. And I think I shut up here. Thank you so much. Well, I abused it by yeah. Thank you guys. By 15 minutes, which is within the reason. Yeah.
Do you think there are any questions?
Yeah, can you hear Gilles when he asks? Or should I?
Very poorly.
So maybe you come here. Yeah.
Okay, so are there any questions?
It's Ludwig. I have one comment and one question. Short. So one comment, I think that this relation between Milnor, clutching, and fundamental co-representation of SQ2 already appeared in this our paper on instantons and suspensions of SQ2, if you remember, perhaps.
Yeah. But okay, so when you finish,
Okay, and another thing is this in the last formula and the previous one, this in blue, this 2 times 1, this comes from this direct sum of L1 with L minus 1, or this 2 times, no.
Okay, let me go back to the definition of this Milnor connecting homomorph. You see, here the formula is IN, where N is the size of A. And in this case, A is a fundamental representation of SQ2, so it's a 2x2 matrix.
Yeah, we had this, yes, okay.
I have to write you. I have to write 2. Okay, so now let me comment your comments. The thing is that here we do not assume that the locus of the gluing is the same as the structure group. Okay, this is a redundant assumption. In this case, that's a completely general and new theorem. But I totally agree. In fact, it all started in my old work with Elmar, when we simply well, this was Elmar's idea. I was computing these associated Hopf-line bundles. I have a standard quantum Hopf vibration. I was computing them directly from the winding numbers, and I classified them by the index pairing. But Elmar proposed something else. He said, look, what we can do is the following. We have a piecewise cleft situation, and basically what you can do, you when you look at the Podlesh quantum sphere, it's what? It's the gluing of a quantum disk with a point. But before gluing quantum a point, you can wind the boundary of a quantum disk on itself as many times as you want. And somehow this winding before gluing, this is this Milnor clutching, okay? This corresponds back to the winding number of the representation. And we have it in our paper with Elmar. And it gives another way of classifying these associated vector bundles for the standard quantum Hopf vibration. So that's the idea which is over here. And we are using instantons, so it's basically the same story because from join, right? It comes from join, and you when you do the join, say G join G, right? And then this is a G principal bundle, and then you divide G join G by the action of G. So what will you obtain? You will obtain the double suspension of G. What is the double suspension of G? It's exactly gluing of 2 cones of G, but the cone effect over G. So sort of the locus of the gluing for the quotient when you take the joint construction is exactly the same as the structure. So this is our context. This was in our paper. And for us, it was SUQ2 or whatever of that sort. Yeah. But of course, this effect is exactly the same for any joint construction. But we realized that it's completely general. It has nothing to do with the joint construction. It's just about piecewise. So that's if you want the up. Yeah.
Okay, very good. So thanks. Another thing is just for physicists. Classically for SU2, L1 plus direct sum L minus 1 is trivial bundle. And here, do you know, it's not trivial.
No, but this is a very good. And I didn't answer your question. Sorry. Yeah. You see, in Florianopolis it's very early, so we can keep on discussing it. It's like 3 p.m. We are very happy to. It's perfect working time. It's 5 a.m. in Sydney, so it's very hard. I might probably fell asleep now. Okay. So Ludwig, say it again what you mentioned, because by joking.
Direct sum of L1, L minus 1 tilde is trivial for SU2, but for SUQ2 it's not trivial, probably.
Okay. The thing is that when you push them down onto this sister algebra here, they are trivial, but they are not trivial. Okay. Remember that you see you have this decomposition into the direct sum, right? And I'm giving you here this L1 plus L minus 1 minus 2. So if I would put it in here on this sphere part, this will be 0, as it should be, because it's a direct sum. So these bundles really become trivial of rank 2 when you restrict them to CP1. That's like in the classical field. That's exactly what happens. And to answer your question, Eliezer, so why do I have this convolution inverse? Well,
to make A invertible.
Well, for starters, this also plays a role. But where's this formula? Yeah, here. Okay, right. This is what we are talking about. Well, you need one more thing. I brushed it under the carpet, but by the way I defined it, I'm landing in the Peter-Weyer algebra of A12, and I want to land in invariance of algebra. But because you can prove that the equivariance of a convolution inverse is exactly opposite to the equivariance of your initial map, when you have something convolution with something inverse, then this lands in the invariant part. So this is, if you want Hopf algebraic explanation, that I really land in the invariant subalgebra in B12, not in Peter-Weyer of A12, but actually in B12. Okay. Because remember, this is B12. I brushed it under the carpet. It's not obvious. This is part of a theorem that this is in B12. Okay. If you look at it geometrically, it's the following. This is, after all, a certain clutching of two trivial bundles. Okay. So when do I say that my bundle is locally trivial? When I have a local section. But imagine that my two open sets, or closed if you want, over which I trivialize my bundle, they intersect. Okay. So when I look at the bundle over the intersection space, I have two different sections. Okay. And what I have to find is, for every element in the base, I have to find an element G, a unique element G, because action is free, which maps one local section to another. So this is like a map which goes from this intersection base to the structure group. When you dualize it, go from the Hopf algebra to B12. Yeah, that's exactly the map that you have. And somehow, that's the geometry behind it. This is gluing together two different local sections, which over the intersection do not coincide. Yeah, you have to put them together, and you put them together via this, it's called transition function in differential geometry. Yeah? So in order to get the transition function, that's just a typical formula of a transition function. And algebraically speaking, what you are doing here, you just need to land in fraction invariance. I just recalled, so let me ask myself a question. I somehow mentioned it maybe even in the abstract, is when you go to this final page, okay, what we did with Tomek, we computed this directly using strong connections. Well, we can do it, right? We computed separately projections here and projections there, right? And because we have a pullback diagram and we have this general formula of Elmar Wagner of how to write a strong connection, having strong connections on the pullback pieces, on the pieces giving the pullback, okay? We had more or less easily given strong connections on these pieces. And then by the formula, which is in the paper of Elmar, we got a formula for the strong connection on the pullback algebra, which is this S5 here, right? And we cranked the machinery, and we didn't have to do the prolongation trick because the formula we have with Elmar is completely general. I don't care about any cleftness. It's the pullback of principal corrections is principal, period, okay, in full generality. And Tomek, if he's not asleep, he can concur with me and confirm. But it took us like 20 hours to compute it, and calculations basically exploded. We needed to go into a special room at IMPAN, which has a 5-meter long blackboard to feed the formula. My blackboard in my office was way too small, and we had these 5-meter long formulas and calculated for 20 hours. Being completely exhausted and frustrated. And then at the end of the day, believe it or not, this 20-hour calculation yielded this. Okay? So it all agrees. So this formula, which I advocated at the very beginning, this theorem with Brzezinski, that, hey, I don't care about Milnor, just use the general theory. Yeah, you can do it. And yes, we did it. And yes, we got this beautiful formula, but it was 20 hours of insane calculation. Whereas here, when we use this trick of homotopy, homotopy is fundamental representation to elementary unitary, then compute this. You can do it on a napkin in a restaurant, and you get the same formula. So this is why I'm advocating this main theorem. I agree, Ludwig. I agree that this is infinitesimal progress, and also this theorem is easy to prove. So it's not like a new result, but this is an important conceptual tool that allows you to do real life calculations much simpler and much more effectively. And this is why I was digging so deeply into these examples.
Okay, thank you.
Tomek? Hello, Tomek.
Yeah,
yes.
Hello. Thank you very much for the... You mean which Tomek?
Well, I mean Tomek, who is not in Sydney.
Okay, so that's probably me. Well, I'm mentally in Sydney for some reason, but never mind. So if you go back to slide 13, and you just answer the question
here
about gamma 2 inverse, can you put gamma 1 inverse and gamma 2 not inverse and get something sensible, or it doesn't make sense? Or it's important that pi 2 is surjective?
Yeah, you answered your question. Yeah, exactly. Here it is fixed when we do this Milnor clutching. You see, this has to go into the direction which is surjective. Okay, because this is the way you. Of course, I mean you can redo it. You can flip everything and you can you see have this element on the left and one on the right, and then you can have surjection on.
That's obvious, yeah. Oh, okay, so if you go to slide 11 now, I think it was.
Yeah.
Okay, so you start with a pullback diagram, and then you cotensor it. Do you still get a pullback diagram?
Yes.
But pi2 tensor identity, as you wrote it here, it's not necessarily surjective anymore, right? Unless V is coflat.
Yeah. But this is a good point, Tomek. I'm at this stage. I do not make any. Wait a second. At which stage I do assume subjectivity? Not yet. Not yet. I assume subjectivity only to go to this sort of Meyer-Vietoris setting. So at this stage, I don't care. But you know that when we are principal, we are automatically coflat.
Well, on the but that's not V that is coflat. But you would need coflatness of V because you are tensoring with a tensor functor, cotensoring with V, not with P. In the example, the prolongation, you apply to the prolongation, then it's fine because indeed there's a principal side when you cotensored with was it SUQ2?
Yeah.
So that's all right because then you have coflatness. So that the argument here is fine. But I don't know how general you want it to be.
Well, I'm really using this subjectivity only basically for the pullback of fixed point subalgebras.
Yes.
It's the only place where I really need this subjectivity. And
I mean, in this example, everything is fine because
But I think that in the generality of the main theorem, you see here, where I have because I believe in our paper we really studied this question. Okay, that the assumption that you have surjection here of sister algebras. Well, it also gives you the surjection for fixed point sister subalgebras, and that's all you need for the Meyer-Vietoris.
Okay.
Yeah, and somehow here you cannot do it the other way around, right? Because I suppose if you do it the other way around, you just get the inverse matrix. If you replace the roles of gamma 1 and gamma 2. Because remember that this formula is obtained from this diagram. So I go by lambda 1, 2, and then I lambda 2, lambda 1 to inverse. This is what gives me this convolution inverse. And if I go the way around, I'll just have chi inverse. Yeah. This also shows why this matrix is naturally invertible. When I just replace the roles, here will be gamma 2, here will be gamma 1 inverse, and that's the inverse matrix. So yes, you can do it; it makes sense. But then it's exactly the opposite of this Milnor clutching matrix. Okay.
Okay. Thank you. Thank you very much for the talk.
Thank you, Tomek. I recalled our old theorem. You know how long it took me to remember it.
All days we were young ones.
Maybe from the room.
So if not, let's thank PIOTR again.
Thank you, guys. Thank you.
Thank you.
Let me stop recording.
Thank you.